Hi everybody, and welcome to GoTo10. My name's Aaron, and I am representing GoTo10 here. And I just want to say welcome to everybody here, and just tell you a little bit about GoTo10. I guess a lot of you have been here, or some people not been here before. First time, GoTo10? Okay, great. Well, little thing about GoTo10, we are a co-working space, and you're welcome to become a member. It is a free space for you to use. So if you sign up today and join, you have access to this great place, and you can come here and work, study, and also have meetings, book the meeting rooms. So if you have any questions about the place, just talk to me or Oli, community manager. They'll be happy to give you a tour, show you around the place. But welcome today, and I'm going to pass you over to Anna, who's going to tell you about today's event.
Thank you, and we are very happy to be able to be here at GoTo10. My name is Anna Broders. I work as a talent and community manager at Linköping Science Park. And I would also like to say very welcome to today's Tech Tuesday. Tech Tuesday is a collaboration between a couple of different companies. It is Combitech, Sectra, Ericsson, SICK EVP, and NIRA Dynamics. And today's host is NIRA Dynamics, and I will soon introduce our speaker. Also very welcome for the people joining us digital on YouTube. We will have a presentation, and afterwards there will be time for questions, both in the room and via the chat at YouTube. Today we will hear Thomas Eckestad talk about stateful stream processing with Apache Flink. So I will leave the word and the floor to you. Welcome.
Thank you. Let's see. Okay, welcome everyone to this presentation. Let's see. Sorry? Yeah, okay. So is there anyone in this room that used Apache Flink before? If we disregard the NIRA people. So it will be hopefully interesting for you to hear about it. Yes, so about me, I work as a systems architect at NIRA Dynamics, and before that I've been, sorry, isn't it better to stand here, right? Yeah. Yeah, and I have a background as a software developer, so I've been doing that for almost 17 years, roughly. I've been mostly concerned with back-end development in different programming languages, and I feel passionate about solving problems in, let's say, an elegant way, using the appropriate tooling to really try to find the simple solutions to the problems. And appropriate tooling can be a framework such as Apache Flink. It could be something else like Spring Boot if you're doing Java development. It could be a programming language which is more suited to the task you want to solve than another one, maybe. It could also be that you have the right infrastructure to help you, like proper monitoring, logging, CI/CD, etc. So there's a lot of degrees of freedom in today's software development. So I think it's important to pick your tools. So the agenda for today. I will start with a short introduction about what NIRA does and the use case we see for using Flink, the use case for stateful and fault-tolerant stream processing we have. Then I will dive into Flink to give an overview about what Flink is and the theory behind it, and then I will finish with a demonstration. So NIRA is a company that's been around for, I guess, roughly 20 years. I'm not really something like that. And it started with embedded software running in the car. So it just within the car. And we don't build any hardware at NIRA. It's purely 100% software. So the first product was a tire pressure indicator, if I'm not wrong. And with that, we detect pressure loss or variations between the car's tires. And I guess some of you had the indication that you need to go and inflate your vehicles. So this is a software-based solution. There's also a mechanical hardware-based solution for this. But to do this, we collect sensor data from the car, which is standard sensor data. And we have software calculating this stuff. So from this tire pressure indicator, more things have evolved, like friction estimation. So we have software to estimate the friction potential between the car and the road surface, which is something we can use to, for example, detect slippery roads, which can have a number of different use cases. Also obstacle aggregation like potholes or speed bumps. And we also measure the roughness of the road, how to say, uneven the surface is, and also how the surface changes over longer periods of time. And these, let's say, the obstacle and road and friction, those are not mainly of use within the car, but instead, all modern cars now, they send the data to some cloud backend somewhere. And from there we get the data as well into our cloud backend, and we call this road surface monitoring. The data we get from the cars is composed of like small batches of data, basically GPS traces of routes the car has driven together with the output from our software. And we want to support, or already do, we support millions of vehicles, and currently we're in Europe, the US and Canada, but we want to grow more. And we need a solution that can scale horizontally. We host our services in AWS, so we have a combination of we use a combination of managed services on AWS and services we host in Kubernetes, also running in AWS. So, maybe the most important point is that we want to be able to scale on demand. So that's a design requirement for our system. So what do we want to do then? We get this data from all the cars, and we map it to road segments on the map. And we want to track the state for individual road segments. Let's say a segment could be 25-meter section on the road, and we do this for, let's say the whole world. That's the end goal. We need to respond fast to new information. Let's say if a car detects serious slipperiness, it's nice if we can get it, if we can understand that soon and send alerts to the vehicle fleet so they can be warned, like a hazard warning. The same with potholes. We need something that is cost efficient. You can build systems, which I was kind of into a bit earlier, you can build them cost efficient, or you don't. You can always scale up. I mean, in the cloud, the resources are never ending. So, but it's also, it becomes evident pretty soon when working in the cloud that you need to, even if all the resources are there, you should not use them, because then you will not be able to, then you won't be able to pay for your bill. We don't want to lose the state for these roads that we keep. So even if machine failure, hardware failure, network failure, any failures, if we do an upgrade of the services, we still want to keep the state and preserve the service level we have agreed on. I could also say that depending on the use case, you don't always have to respond fast to new information. For some, like the roughness scenario where you see how a road deteriorates over time, you don't need like near real-time action on that. It's okay if you just get it maybe with a resolution of a day or a week or something like that. Apache Flink, then, it was first release of Apache Flink was 2011, so it's actually been around quite for some time now. Apache Flink is an evolution of MapReduce. You can say that MapReduce is a subset of the functionality offered by Apache Flink. I don't know have you heard about MapReduce? It's a programming model for processing big data sets using parallel and distributed a parallel and distributed algorithm. So the picture on the right, let's see, here illustrates a MapReduce job. So it can be very simple. For example, let's say these blocks are information about the person. So in the map phase, you could map some property on that person, like the first name maybe. So let's say all persons here with the same name ends up in the same queue. And then there's a shuffle phase. So all these things are happening on different machines. And they are only connected through the network. And then you make sure that, let's say, here we get just an array of names like Ben, Bob, Alice, Rob, something like that. In the shuffle, let's say we want to key on the name, then we collect all names which are the same in one queue, but they will end up on a different machine. So that's a shuffle phase. And then the reduce phase, you can perform an operation on the names. So in this case, these queues will just be an array with one entry. Let's say there are 10 robs, and there will be an array of 10 robs here. So you can, for example, reduce it. A reduce operation could be to take the length of it. It's a very simple example, but it doesn't have to be more complex than that. So it's a way to compute, to solve a problem in a parallel way, because there are really no dependencies between the map data. Yes. So back to Flink. So Flink can do this as well, and a lot more. MapReduce was originally introduced by Google in 2004, so a lot has happened since then. I guess some of you heard about Apache Spark, for example, which is also an Apache Hadoop, of course. Those are also very big players. But Flink is the newest of them, and Beam is actually just an extension of Flink. And there are some even newer stuff which is not in this slide. So there's a lot of different tools to choose from in this area. So Apache Flink is a true streaming engine compared with, for example, Apache Spark, which in reality works on batches. Flink processes one message or event at a time. There are APIs for working with Flink in Java, Scala, and Python. And there's also a SQL API. So I think the main competitor to Flink in the open source world, at least, is Apache Spark. Okay, so let's jump into something a bit different. So with event sourcing, so why am I mentioning this? Because I think it helps to understand the origins of where Apache Flink comes from, and other stream processing engines as well. And it also ties closely to the role of the event log, which is kind of mandatory when using Apache Flink. You need some kind of event log. So it's very much inspired by event sourcing. So what is event sourcing? I think it's very common that you build your system based on CRUD, create, replace, update, delete operations. And when you do that, you don't, the system doesn't know how it ended up in the state it is, only which state it is in. And the idea with event sourcing is that you, instead of applying the CRUD operations directly, all source data is in which drives these operations are inserted into event queue, which is immutable, so you can only insert it to it. And then everything else is, these CRUD operations is driven by this event log. So it's not really that, the difference isn't super big really. You just introduce an extra level of abstraction. So you get an event, you store it in an event store. In the relational database, that would be a table. And then you define preactions, which is data working on events from the event stream, producing preactions, which can be tables in the database or something else. Something which can be built from the event log, from the state. And this approach has a number of benefits. For example, let's say you want to if you want to somehow, for some reason, you need to rebuild this, or you need to maybe reinterpret the events in some slightly different way. So instead of trying, like within this system, to update it in place, you can update the preactors, and then you can hopefully just clear this database, and then you can replay the event from the start. So you can rebuild the history. Another nice aspect of this is that you have the event log. So you have a log about everything that's ever happened to the system, when it happened, and so it's maybe a bit easier to reason about in some cases. Yeah. Of course, it might not be possible to really replay all of the event log. It might incur a lot of cost for computation resources to do that. But you can also, you don't have to do it all or nothing. It could be a combination of both. Yeah, I included a slide about Apache Kafka. We use Kafka as an event source or when we use Flink. And they typically go really good hand in hand. So Apache Kafka is a message queue, a distributed message queue with fault tolerance and which scales horizontally. So it scales basically to whatever needs you have. You can so it's based on queues where you just put data, and to be able for it to be distributed, you compute a key for each event or message you put in the queue, and based on that, the message ends up in the right partition. So you can be many partitions for one queue. So that's a deterministic algorithm, so all messages with the same key or hash ends up in the same partition always. And you can increase the number of partitions or decrease them and scale it basically however you like. A difference between a message queue such as Apache Kafka and a message broker such as RabbitMQ is that the consumer does not own the message it gets. It only gets a copy. In the message broker just help you with sending a message from a producer to a consumer, and then the message is gone. So with Kafka, the retention of the data has nothing to do with when you consume the data. That's a total different configuration option in that case. Let's see. Yeah, this is another picture just illustrating a traditional application using let's say a relational database, a transactional database. And you issue, write, read, like SQL, insert, update, and selects. But with Flink, the database is the application, and these reads and write are, you basically access the state as you would any other variable in your program. So it's not transparent to you if it goes towards storage or not. Which also comes with a risk, of course. So you need proper monitoring to see how your application performs. That's very important. Yeah, I mentioned Apache Flink is a distributed system, so it's only one Flink instance here, but in reality there can be many. It can be hundreds or thousands instances. And it's pluggable, so you can pick this is called a source element. So you can pick your sources, and this is called a sink. So you consume data from the source and you produce them to a sink. And this can be whatever. It could be a file, it could be a Kafka topic, it could be a NoSQL database, it could be HTTP. It's also, as you do with a relational database, you have a database schema, which you can evolve your database schema. You can do the same in Flink, but in that case, the schema registry lives. It's also a second service, which you can use. And in that case, yeah, you can evolve the schema as you could in a relational database. You also use local storage, which is close, attached to the node where each Flink instance is running, basically, which should typically be fast. That's kind of to compare with the write-ahead log if in a relational database. And there are periodic checkpointing, also a concept that comes from relational databases, where you take your local storage and move it somewhere to cold storage, which you can do point-in-time recovery from if you need to. So let's say there are 10 Flink instances and it would be 10 versions of the local storage, but this one would be the union of all these 10, the data from all these 10 instances. Yes. Yeah, the state backend in Flink, it's pluggable, so you can replace it. There are, I think you can say that there are 2 options for using a production, depending on if your application is memory intensive or not, and also depending on the performance you expect from your program. And you can switch these backends not during runtime, but you can you can save the state to disk, to the cold storage I showed you in the previous slide, and you can switch state backend and you can restore from that. You can get in-memory computing, Flink tries to unify batch and streaming, which is kind of one of the things that where Flink stands aside from the other competitors. Yeah, and also an interesting thing I think is that it encourages building scalable single-threaded applications. At least I like the notion of event-driven applications where if it's possible to use something else than a model where you use threads and explicit thread synchronization, I think that's very nice, more like a message passing model. So, and Flink is a good way to enforce that kind of development practice. Okay, so I will try to do a demo of Flink. And the purpose with this demo is to give an idea of the power of Flink, what types of value the Flink framework brings. I try to keep the demo as simple as possible. So I actually use this Flink Playgrounds, which is on GitHub, which you can try out if you want to. It's very easy to get started with. It's based on Docker Compose. So you can basically just do Docker Compose up. And there are 3 different playgrounds to try out. And I'm based this theme on the Table API playground, where you actually use SQL to implement your Flink job. We don't use the Table API at NIRA, but it's maybe we should, I think, for some simpler stuff. And it's very, if you worked with relational databases before, it should be easy to get an understanding of what's going on. Let's see. That's my point. Okay. So nothing is running right now. So I will start, and I'm standing in the table walkthrough. So I've based this on this demo on the playground, but I've done some changes to it. So what I did now was I spawned up a Kafka cluster, which consists of a job manager and a task manager. The job manager is the orchestrating part, so it kind of dictates what the task manager should do. There's a data generator just outputting a stream of data. In this case, very simple CSV structured data, which I will show you. And there's the Kafka. So the data generator produces CSV data and places it on the Kafka topic. And the idea is that we should create a Flink job which consumes this data and does something with it. Let's see. Copy and paste. So what this does is I run the Kafka console consumer. So this just peeks at the Kafka topic, which gets this CSV data. So you see, the first column is a transaction or account ID. It's a number between 1 and 5. Then there's a number, just a sum, and then there's a timestamp. And the generator just keeps inserting this, and it's just the date just increases forever. So now that we know that the messages are on the Kafka topic, so we should start up. Yeah, and there should also be possible to see Flink. Flink comes with the UI. So this is the one started by Docker Compose. We have so this is a Flink cluster. There is nothing running on it right now. We have a job manager and we have one task manager. So the next step is to create a job and post it to the Flink cluster. So to do this, okay, it didn't solve. Sorry, but I just there's a SQL client's binary on the included in the Flink distribution. So what I did was just to execute that binary from the job manager Docker container. So we'll start with a simple query just to see that things are working. And I set this to batch mode because this will be a query with a simple result. Let's see. So what we do is we do a select from our own table we build up here. It's just a table with 4 names, and we group by name and count them. So when I run this, you will see that there will be. I don't mind the warning. You see, now there's a job running here, and now the job is done, and we got the result. So we managed to post that query to the Flink cluster, which started a new job and gave us a result. So let's do something more interesting. Switch to streaming. Streaming means that the query will never end. It will just run indefinitely until you interrupt it. So the first thing we will do is create a table which we map towards a Kafka topic. So this looks very much like the traditional relational database table. We create a table with number of columns, and we also tell it how to handle the time. That's I think I haven't mentioned that. That's a key thing in Flink, that you can use the time in the data stream you're working on to define the time. So we say that the transaction time should be used as the time as driving the time in a Flink job. And we say that things are allowed to be up to 5 seconds late before they are considered as old data. And we use a Kafka connector, and we specify which topic we want to connect to, how we connect to the Kafka cluster, and if we want to read everything on the topic or just start from the latest. So this will just start from the most recent message put on Kafka, and we tell it which format the data has on Kafka. So now that table is created. So we could so this will start up a job, as you see here. Can even look at it, and this will just, when I use the console like this, it will just take a snapshot and update it once in a while. And you can actually see what Flink is doing here. As you can do, like explain on a relational database, you have the same thing in Flink. It has a query planner. So this is very simple query. But it says something about what the job is doing, what parallelism it's running with, if it has trouble keeping up, etc. So we know that the table is working. We get the data from Kafka. So we want to do something a bit more advanced. Let's see. So what we do here is that we group by transaction time, truncated to hours, and we sum on the amount, and we group by the account ID. So this is, very similar to a traditional group by in a relational database, except you group on the time level as well. So it should show up here. I hope. Yeah. Now you can see that it's only even hours. Sorry, it's too narrow. And this is summed amount, and you get one result per hour. So this is a streaming job running forever. So let's move on to the next step. In the examples I showed up till now, we've just been dumping the data to the console, but you could also dump it to another sink. So I create a table which I call aggregated transactions with the data we just saw, the summed amount, the count ID, and the transaction hour. And we connect that to an output Kafka topic, which we call aggregated transactions. And we tell the output to use JSON for the format instead of CSV. So now we have two tables, transactions and aggregated transaction. Now we can do post an insert query, which selects data from the source table and inserts the transform data into the output topic. So it's the same query, but instead of select, we also do insert into aggregated transactions. So let's start that one. Now it's running, and it should pop up here as well. So the job is running, and the hash is that's a group by operator in action. So if there were many, or the shuffle I showed you previously in the map reduce. So if there were to be many, like a parallel is larger than one, the data would be shuffled to, for example, based on account ID and the hour. So all combinations of all of the same combinations would go to the same instance in that case. But in this simple demo, there is just one instance. So now we're actually inserting data to the Kafka output topic, we think, but we can have a look. Okay. Let's see. Okay. So now we're peeking on the aggregated transaction topic, which we are writing data to. And you can see that the data ends up on the topic. And it's in CSV format. We can also list the Kafka topics. Yeah, maybe we don't have to do that. So let's switch back to this. Sorry. So that was a demo, and the roadmap for Flink ahead. Machine learning is a very, I think, uprising use case with Apache Flink. You can use it a lot. Also, the Python support is getting better, and also in some case parts the SQL part which I demonstrated now. This is actually in beta. But Apache Flink is one of the biggest projects of the Apache Foundation. So things are happening. A lot of things are happening all the time with the Flink. Yeah, that's it. Any questions?
What's the best feature with this new solution compared to what you had before? What's the best feature?
It's just, I would say, it does a lot of the heavyweight lifting for you. For example, the event time is a great thing that you can base the time of the job. For example, you can set a timer to expire, I don't know, in the future, which is not based on wall clock time. I was part of developing a system similar to the traditional CRUD system a number of years ago, and we did a number of mistakes, but mixing or not only using event-based time, that is time from the data source, was a big mistake. We used also wall clock time, but with Flink you have the abstraction to use event time for everything, which is great for timers and such things. And also, it provides a lot of abstractions that you would need to implement yourself otherwise, I would say. and it doesn't. I mean, it doesn't have to replace relational databases if that's what you're using for this. It could be a complement to it as well. So the Flink state is not really supposed to be queried. It's just internal working state. So if you want something queryable, you should generate that data to another source for that data outside of Flink. And also it does some really, hard stuff. Flink can guarantee exactly once consistency if you want to. With Kafka, you can get a guarantee that each event is processed exactly once, which is really a hard guarantee to give. But Flink can do that. But you can also tell Flink it's configurable. You can also say, okay, it's okay if I process each message at most once. And Flink will support that use case as well. So it's very adaptable to the use case you have. But it's not solving all of the problems in the world, but the problems it tries to solve, it solves good.
Thank you. Do we have any questions in the chat? No. Any other questions in the room? Yes.
What about the economic side? Once you started using Flink, has it proved to be lesser bills that you mentioned earlier?
When it comes to NIRA, actually, they've been using Flink from the start. But a key point with Flink is that you can do incremental instead, as you would with a typical batch job. You kind of reprocess the same data. You could have overlapping data as a source for a batch job. But with Flink, you keep the data in memory, so you can just do incremental updates. And it's usually much cheaper to do that. Both performance, you don't need the same resources, the computer resources. So, the key with saying that it's cost efficient is that you can do things without, you only do what you need to do. You don't take omvägar to do it. But I think if you pick the right tool for the problem you want to solve, it will be cost efficient. You should not pick a tool just because you have used it before for something.
Great, thank you. I think we will wrap up now. But if you have any more questions in the room, I hope Thomas will be able to stay for a few more minutes, so take them directly with him. First of all, a big applause for Thomas for this presentation. Thank you, and thank you all for coming. I would like to welcome you as well for the next Tech Tuesday, which will be the 25th of April, and then it will be hosted by Combitech, talking about smart factory and digital transformation that's always centered on people and security. So I hope we will see you then again. Thank you for today and have a nice afternoon.